This is in some sense a summary, a little bit more detailed, of the particles in the Standard Model with some of their properties, their masses. For instance, you see on the right-hand side these masses. So there are always these kind of two feelings you have if you're confronted with this. First, what a terrific power of ideas. Simple mathematical structure and a handful of particles explaining everything we see around us here, really every physical effect. And then the second question is, okay, so tell me more about it. Tell me more about the parameters, about the properties, why this particular group. And then you get this famous question that once was asked about when the muon was discovered, who ordered this? Why these particular particles? Why these masses? Why these properties? Why does every matter come in kind of a family? And why do we have three of these families, roughly small, medium, large? Why the groups, indeed, SU3, SU2, U1, they might have some special properties, but are they totally unique? Is there some kind of intrinsic way why nature picked this? So it's almost like we understand some of the physical laws. We know the law, but then the question is, what is the specific solution to the law? Newton's laws of gravity are universal. Our solar system is just a specific example of that. How unique is this model? And there are many questions about this. And so people speculate. For instance, if you look at the particles and antiparticles, and you use the fact that we just learned about, that neutrinos have a small mass, which was kind of totally unexpected and doesn't fit within the standard rules of physics, within the Standard Model, you have to presuppose, if you can presuppose, another neutrino, a very heavy neutrino that I put here on the right-hand side here. It's a particle that we haven't discovered. It might be there. If it's there, it's probably very, very massive. But then the theorist mind takes over, and people look at this diagram and say, well, look at these particles within a single family. Can we rearrange them in a nice way? And for instance, they can be rearranged in this way. This is a kind of a 5-dimensional hypercube. And this suggests that there's a bigger symmetry, that there is a symmetry, what we call the grand unified symmetry, a symmetry group that would contain, as a subgroup, the U1 cross SU2 cross SU3. But for instance, here is SO10. Now, whenever you do this, whenever you unify, that's a familiar pattern. You unify, so you simplify, but at the same time you produce also more effects, and you're also predicting more effects. Time of time we have seen this. So any of these attempts to unify the Standard Model will actually give suggestions of other particles. And so you have to find a good explanation why you haven't discovered the particles. They might kind of mess up some of the wonderful properties that the Standard Model has, namely that it's quantum mechanically consistent, there are no so-called anomalies. It's kind of really a very fine-tuned Swiss watch. So if you start to mess with it, you have to be careful not to destroy that. But this is a line of thinking about bigger symmetry groups that in some sense are broken in the same way as some of the symmetry groups of the Standard Model are broken. Well, we already heard a lot about dark matter. Clearly, this is something which is outside the Standard Model. So any theory that predicts new particles is certainly, we need something like that because there's a huge part of the universe. We aren't made out of it, but it's out there that has to be explained. And we also learned about the dark energy being there and how much actually is not yet explained. So I think theoretical physicists have these two frames of mind. They really want to understand in more details the theories we know. But we also know that in some sense this is preliminary. And perhaps any progress is preliminary, but we are in a very interesting point because we're on the threshold of understanding the 95% of the universe that's still out there and unknown and not described by our theories. And in the same sense, our theory is also crying out to be extended. And perhaps the two things can go together and we really can push beyond what's known at this moment. And I think it's also important to realize that that's one of the aims of a theoretical physicist. You like to predict or to map out that part of nature that's not yet mapped out. And by the strength of ideas. So one thing I want to emphasize with you is that there is this great phenomena that here are depicted the 4 fundamental forces of nature, the 3 forces acting on the elementary particles, electromagnetism weak and strong, and then there's the gravitational force. And this animation shows how these forces change their character if you move to higher and higher energies. And I actually want to explain how this happens and why this is important. But the great thing of physics is that it's not as invariant as you might think it is. And I want to go back to a very elementary question. It's another of one of these why questions. So think about electromagnetism and think about the strength of electromagnetism. So take two electrons and measure their force between them. Well, it goes as like 1 over r squared. There's a good reason for that. In modern parlance, you would say that's because we have a massless particle, a photon, interacting the force. But then what is the size? What is the size of the strength? And there's a coefficient there that you can compute. It's proportional to the square of the charge of the electron. And it's called the fine structure coefficient, and the mathematical symbol for it is alpha. And so the question is, how strong is the electric force? And you can compute alpha if you know what the charge of the electron is, and you find it's roughly 1 over 137. Now, for a long time, people actually thought it was exactly 1 over 137. And you can find many papers in the past that people were really fascinated by the number 137. You know, why 137? There's a famous stories of Pauli, Wolfgang Pauli, famous physicist, at some point at the end of his life, was in this hospital room, which is number 137. So he was really spooked by that. In fact, there's a great story, perhaps you know, about Sir Arthur Eddington, the one who actually verified the solar eclipse and the bending of the light and made Einstein famous. He had, in the later phase of his life, a theory about the universe. In fact, he thought he could compute the total number of particles in the universe, which was the formula over there, 136 times 2 to the 56, because at that point, the fine structure coefficient was thought to be 1 over 136. Then the measurements increased, and he actually then got more like 137. And then suddenly he realized, oh yeah, of course, I had to add 1. And then famously, he was described as Sir Arthur add on 1. But what's the modern point of view? Actually, here are the numbers. You see the number on top, which is the experimental value. It's less than, with an uncertainty less than 1 in a billion. And then there's the theoretical calculation below. I think it goes up to 10 loop diagrams, Fermion diagrams. So I think there are tens of thousands of these diagrams that you have to compute in order to calculate. So it's amazing. I think we should emphasize this, that if you want to find an area in physics that is really well known and experimentally verified to large precision, you have to go to the area of elementary particle physics. The precisions you find there, I would say only perhaps in mathematics, where things are either 0 or 1. Nowhere else, I think, you find these kind of precisions. But what's the modern point of view? The modern point of view is an amazing thing. The fact is that the strength of the electric force is a function of the energy by which you measure it. So we have particles, give them a certain speed. For instance, if they're circulating around in these accelerators, an electron going around an accelerator, as it did, for instance, in the old lab experiment, had a larger charge than the ones, a squared, smaller charge than the ones at room temperature. So, a crazy thing, the properties of matter change depending on which energy they have, or, by the way, another way to put this is, if you think of high energy experiments as looking through a great microscope, it's the amount of magnification that you choose will change the properties of the force. And one way to think about it, that if you take an electron and you put it in space, there's this whole fluctuating sea of elementary particles, virtual particles, coming out of nowhere and disappearing again, that is changing the properties. And if you look closer and closer, this effect is stronger and stronger. And the electron is being shielded. That's not something what happens. So these properties change, and it's quite dramatic. For instance, if you do this for the strong nuclear force, it has the opposite behavior. If you go to higher and higher energies, the strength of the force becomes weaker and weaker and weaker. And this was one of the great achievements in theoretical physics that was honored with a Nobel Prize relatively recently. And so if you then look at the 3 forces in the standard particle, and you follow them up higher and higher energies, you see that their properties change and they're converging. It looks like they really want to be the same. And there's an area, many, many orders of magnitude away from where we measure them at this moment experimentally, because this behavior goes with logarithmically in the size of the energy scale, you see they're almost passing through a single point. And one reason why we're enthusiastic about this, because it looks like that if you have a fundamental point of view at very high energy, that these might be perhaps three elements of one unique phenomena. And the plot becomes even better if you include another symmetry that I now want to mention, which is supersymmetry. So the question with unification always is, is it in our minds? Is it just, are we obsessed that we want to describe nature with one line? Are we obsessed that nature, we should have a single formula describing everything around us? Or is it something very deep in nature that nature herself wants to describe in simple ways? So looking at these plots, we see this as a strong hint that there might be something going on at very high energies which look deceptively like unification. Now, I mentioned supersymmetry, and supersymmetry, we saw some of the experimental consequences of supersymmetry in Maria's talk, but how do you think of it as a theoretical concept? I would say supersymmetry is the only symmetry that we haven't observed in nature, but we know it's consistent with all the other things we know about nature. So if you say, give me the laws of physics, can I improve upon them? Can I think of something that's not yet used, that's consistent with all the laws of relativity, of quantum mechanics, etc.? Supersymmetry is the only thing that we know. And in fact, as a mathematical proof, it's the only thing that you can add to it. And it's a very strong, I wrote down here the algebra, the supersymmetry algebra, but it's relating two things, literally the two halves out of which we think nature is composed. So on the one hand, we have our forces and fields. Technically, these are particles with an integer spin, and we know the spin can be at most 2. So there are three cases, 0, 1, and 2. And nature uses all three of these options. Spin 0 is the Higgs field. Spin 1 are the usual force fields. And spin 2 is actually the gravitational field. I will say something in a moment. It's the graviton. And then you can have half-integer spins. And if something has half-integer spins, it behaves like a matter object. It's something, there's a fundamental principle that says if two objects have both half spin, it's the Pauli exclusion principle, they cannot be sit on top of each other. That's why you can sit on your chair, because basically your electrons and protons cannot sit on top of the electrons and protons, or cannot be at the same spot where the electrons and protons of your chair are. So that's why you, out of half-integer spin, you make something which is like matter, while of integer spin, they can be on top of each other, and that's why you can make a laser beam out of light, which is essentially a huge number of photons, which are all exactly the same, or exact clone of each other. In fact, it's describing spin and half particles, so describing all our matter particles, and the only theoretical option open in nature is to have a spin 3/2 particle, which would be like the super partner of the graviton, of the gravitational field, and would come with any supersymmetric extension of the world. So both in terms of fundamental principles and both in terms of the matter, there are two vacancies, which we are very much hoping nature will fill, because otherwise you will have a very strong, and we don't understand what kind of argument, not to make use of this principle. There's sometimes a saying, in nature or in quantum mechanics, anything allowed is obligatory. Nature basically pushes every button that you can push. It's like a small child. You're just pushing everything and using all that's out there. So in a more theoretical way, one way to think about supersymmetry is that there's another dimension in space-time. Now we think of space-time as described by coordinates x1, x2, x3, x4, like time. They are real numbers. They have a property we find absolutely obvious, which is just a number that 2 times 3 equals 3 times 2, which we say it's commutative. And in fact, in everyday life, we only use commutative numbers, so that's kind of obvious. But mathematically, you can also have non-commutative numbers. Nature used non-commutative numbers to describe our fermions. So if you want to, there is non-commutativity, which would be something like 2 times 3 would be minus 3 times 2. Would be kind of quite bizarre. But this can happen, and it seems nature likes this option. So you can think of, suppose we have an extra coordinate, which is a supercoordinate. It would be like pointing away from space and time, But in a very funny way, because if something is anti-commutative, it basically squares to 0. So in terms, it's almost like an infinitesimal in the old fashion of Newton and Leibniz. With something that is, if you squares, it's 0. So you can take an absolutely minimal step in this other direction, but if you take a second one, it stops. So there's a very thin layer, in some sense, to nature. And that would be the way to describe it. So nature would have, in the same way as the realm of particles is nicely symmetric, having both bosons and fermions, commuting and anti-commuting objects, space-time itself would have that property. But again, that's all speculation, because we have seen that if you would have a theory of supersymmetry, we have to find many, many particles. Every particle would have a mirror particle, and none of them have been found. But in some sense, what I now have told you are basically the whole arsenal of ideas we have. So this is our toolbox. We can have extra gauge groups. We can have unification of groups. We can have anti-commuting variables. We can have supersymmetry.